He's a good boy.
Yeah. Okay.
No, my dude. What time is it? God, it's time to go.
Okay, number 6. Whole bunch of these limits, they all have something in common. They all say, what's the limit, not as x approaches a number, but as x approaches infinity.
Plug in the old infinity. I'll love you forever.
How do you plug
You can't really plug in infinity. So
He just kind of looks you and sees
you gotta just, the trick to this is thinking about end behavior. So if you understand end behavior, these are really actually pretty simple questions, because this question, I can rephrase it as, what is the end behavior of the y equals 1 over x function as x approaches infinity? And that's literally what it says, is what happens to this as x gets arbitrarily large. So what's the answer to this question?
It approaches 0.
0. So the answer is 0. There you go. You're going to find a lot of these questions have an answer of 0. Yep. The answer is 0. Now, does everyone understand why the answer is 0?
Yes.
No? Okay. So would you be okay if I just said the answer to this question is 0?
Yeah.
But would you be okay if I asked you, what's the end behavior of this function? So y equals 1 over x. This is one of our parent functions that we hopefully have a pretty good understanding of. This function does this. So would you be okay if I said that as x gets really, really big, the y values get really, really close to 0, like way over here?
Yeah.
So that's what this limit is saying. It's saying what happens to this expression as x gets really large. Now, if you get stuck on a question like this, there's certainly nothing wrong with taking a numerical approach. And by numerical approach, I mean, let's think of some x values. Let's think of a big x value, like, that's terrible. Let's say x was, I don't know, what's a big number? 1,000, a million? Let's go 1,000. If x was 1,000, then 1 over x would be 1 over 1,000, which is, what kind of number is that?
Small one.
And it's pretty close to 0. I could say it's approximately 0, right? I got 1 Snickers bar. I got to share with 1,000 people. You're going to get pretty much. You're not going to get much. You're going to get pretty much 0 Snickers bar. So what?
I said that's why Coach gets himself.
Okay. All right. Do you guys feel okay about that? All right. Let's answer the next one. What's the limit of x over x plus 1?
Oh, okay. So thank you.
Similar situation.
Okay, let's answer this one. Let's say x was really, really big. What would this be approximately equal to? 1. Why is that? Let's think. Is this like a famous parent function that we just know by heart? Probably not, no.
But you can just look at the thing.
Yeah, we could graph this, but here's where it gets kind of circular. In order to graph this, part of graphing this is figuring out that the end behavior is approaching 1. So it kind of begs the question, right? It's like, so what I'm saying is I'm not going to solve this limit by graphing, right? Because to graph it, I'd have to already know the limit, effectively. Is this making sense? Or no?
Yeah.
Yes.
Okay, so thinking numerically, again, let's plug in 1,000. 1,000 divided by 1,001 is really close to what? 1. In practice, though, I want you to try to move away from actually plugging in a number. What I really want you to do is is think about dominant terms, right? Who's the dominant term on top? X. Who's the dominant term on bottom? X. What's X divided by X? 1. Okay, makes sense? Plugging in 1,000 is fine when it's this simple, but if the top has more terms, the bottom has more terms, you're going to really complicate things. So what you want to do is really focus on the dominant terms on the top and the bottom.
So like we should look at C.
Okay,
or
let's look at
E.
C.
Well, I know that like what it would look like is I don't know, you figure it out or something.
Yeah, so let's say that's a great thinky winky right there. Is if you didn't hear what she said, well, I know what the graph looks like. So by the way, what's the answer to this question?
Infinity.
Infinity, or I mean, is infinity a number? No, so I can say the limit does not exist.
Oh, really?
Yeah, if something approaches infinity, the limit doesn't exist. Could you get away with saying that this limit equals positive infinity? Yeah, you could say that. That would be fine. But so Paige said, I know the graph, but what if I didn't know the graph? How would I solve a question like this? So this is where it gets a little tricky, but you have to ask yourself, is there any limit to this growth? Does this thing ever stop growing? Does it hit a certain like ceiling where it can't like go bigger than that? The answer is no. So, and the way you can kind of reason that out is, let's ask ourselves, is there some point along this graph where this will hit, I don't know, someone give me a big number that we might be wondering, when does it hit that number? $1 trillion, okay?
790.
You see what I'm getting at? I might be asking the question, does this graph ever hit $1 trillion? The answer is yeah, when X is $1 trillion squared.
That's a big number.
Which is a big number, but it shows that you can name any number you want, and I can always come up with a number that is going to make this expression hit that value that you said. Cool beans?
Yeah.
So, whereas this one, this thing is never going to, for large X values, this thing gets closer and closer to a single number, 1. For large X values for this, it just grows and grows and grows and grows. It never stops growing. So are we okay with that? You sure?
We should do E.
Okay, sure. Well, how about D? Let's look at D. Let's not fly off the handle here, okay?
Sorry.
D is a cube root function. Does that thing ever stop growing?
No.
A cube root function?
So, I feel like we have negatives involved now, right?
Not really, because it says as X approaches positive infinity. So that's where I mean, let me clarify something here.
I think that it would be infinite. Like it doesn't exist.
You are
because-
correct. Yes, May is correct. Yep.
Done it again.
So let me look at, so watch this, guys. This is a question you could be asked. Find end behavior of y equals cube root of x. This is a question we've answered before, right? So the answer to this question would be, as x approaches infinity, y approaches infinity. As x approaches, here's your negative numbers, Colin. I think this might be what you're talking about. So this is the answer to that question. Now look at the similarity between this question and this question.
So it's just using the positive portion of it.
Yeah, so this is just literally asking you, what's going on here? What's the right side end behavior of this function? That's all it's asking. So if you're approaching a number, that's the limit. But if you're approaching infinity, you'd say the limit doesn't exist. Okay? How about E? What happens on E as x gets really, really large?
It gets large too. So
No,
no, it doesn't.
that's smaller
It gets-
than 1.
well, it gets smaller, but like the x. Does the -1? Can you just cross it out and kind of ignore it?
Well,
Because if
a
x
trillion squared minus 1 is pretty close to a trillion squared.
Wouldn't it just
right?
approach 0 then?
yeah, because it's just like a.
Exactly.
The 1 doesn't grow.
So guys, once this clicks for you, you're gonna realize that, yeah, these are way easier than the graphing ones because, no, incorrect, Colin. Incorrect. Don't infringe my freedom, Colin. I have to tax your bootstraps.
I don't have them. You can't tax them about that.
Yeah, so guys, look, think about the difference between this question and the question that says graph that function. To graph that function, I gotta identify things like, oh, maybe it's even or odd, are there vertical asymptotes, what's the y-intercept, right? Are there any x-intercepts? I gotta answer all these questions and then put it all together at the end. But to answer a limit, I just have to do, it's like what Paige said, it's like, well, the bottom has this x squared, and then does this -1 really affect, if x is big, if x is 1,000, it's -1, right? You can pretty much ignore it. And so what's going to happen if you have 1 over a gajillion, right? You're
So,
gonna be very
Are
close
any
to
of
zero.
these going to be affected like with like x going to infinity? Will any of them be affected like, let's say, because like you know how absolute value, actually never mind. I guess I'm just saying like, will it affect if there's like if it's shifted down 1 or something?
Certainly. Let's look at m. M.
It's fun.
2 plus 1 over.
Yeah, so what's the limit? This is another one. You can think of this one graphically, or you can just think of it numerically. What's the limit of 2 plus 1 over x as x gets really big?
Or would it be 2?
The answer is 2.
It's because it's just like it's just like A, but it's shifted over to the left.
Because the bigger
Shifted
number you
up.
get, the smaller the fraction is. So it's just getting closer.
Yeah, so you can think of this graphically as, I know the limit of the 1 over x function is 0. So if the whole function was bumped up 2 units, I would just be approaching 2. Or think of it in terms of like, let's plug in a big number here. Let's plug in 1,000,000.
It's basically,
What kind of, 2 plus 1,000,000
it's basically 2.
is basically 2. It's pretty close to 2. So as x gets really big, this expression here gets closer and closer to the number 2.
So like for n though, that one would just be, would it be 2 as well, or would it be whatever number you're trying to plug in?
Let's look at n. What do you guys think n is?
Yeah, I thought it would be 3, but then I'm like, wait, that wouldn't make sense though.
Why not?
I don't know. Because if you plug in, let's say 5, it's gonna be. Oh wait, no, it is gonna be 3.
Yeah, 5 is not a very big number, but 5 still kind of makes the point. If you plug in 5, you get 2 plus 5/6. It's
Yeah.
pretty clse to 3. Plug in a bigger number like 100. 2 plus 100 over 101 is going to be. What are you talking about, Julia?
The yellow thing overlaps into the blue.
What? On that painting?
So here, all the yellow things. So then you're seeing the
Stupid.
Julia, the art critic.
Is that yours?
I didn't.
You're born in the back.
Sorry, Julia. Just trying to make sure no one gets lost here. All right, let's jump forward and look at one where the answer is not 1 or 0.
Wait, so n is 3?
Yeah.
Okay.
It's 3.
Oh, alright.
And yeah, the last question on this page will be 3 because you've got 2 plus, that second term would approach 1, so 2 plus 1 is 3. Let's look at something interesting. Let's look at 2 more interesting ones here. What do you guys think? So look at 7a.
Look at that.
Think about it. We're going to look at 7a and then 7h.
It is. You get more.
This is looking pretty scary, right? Oh my
Yes.
goodness, so many numbers, so many symbols. Who here would bet
It's one.
$20 that their answer is correct? This one.
Me. Just kidding.
Well, if you don't have an answer, then you certainly wouldn't bet $20, would you?
No.
No.
That'd be a lost bet. I'm saying, who's got an answer that they're pretty confident in? They're like, yes, I feel like I'm pretty sure this is correct.
Is it 4/5?
Nope. 3/4 is correct.
Really?
Very
You
good.
owe Colin $20.
Let's look at this. Okay.
He ignores
Were you talking about this one, Julia? I was talking about this one, the first one.
So,
So you're correct. You said 4/5, right? Yes, you're correct for this. Sorry, it's a little unclear. I was drawing that one while asking about this one. The answer to this is 3/4. Let's see, why is that? Let's say X was really, really big. X is big, right? Big.
Big X.
Big X.
1 million.
Who's bigger, 3x squared or 8x?
3x squared.
3x squared is way bigger than 8x, so I can ignore the 8x. I can say,
That's your dominant term.
yeah, this is the dominant term on top. Same thing on bottom. The 5 is so tiny compared to the 4x squared that we can just ignore it, okay, for the purposes of this. Again, because x is very large. What do you get if you have 3x squared divided by 4x squared?
3/4.
3/4. That makes sense? Like, how about 3 million divided by 4 million? 3/4. Right? And then this one, this will be the last one we do today. So, Julie, why is the answer 4/5 here?
If you like divide the bigger term, after the square root of the bigger term, and then you simplify it, you get 4x squared over 5x squared, which
Yeah.
would.
Exactly. So the key here is, of course, you can ignore this one because it's so tiny compared to this. You can ignore this one because it's so tiny compared to this. Like Julia said, the square root of 16x to the 4th is 4x squared. The square root of 25x to the 4th is 5x squared.
Which is
That's more of an arrow than I can't really say that's equal to that, but I want to be really precise. So yes, the answer to this is 4/5. Okay, do you guys feel okay about that?
makes sense.
All right, so that's pretty much all there is to questions 7 and 8. Tomorrow I'll go over 9 and then 10 and 11. If you're looking forward a bit, you'll see that 10 and 11 are throwing in like exponents, like e to the x and 2 to the x and 3 to the x. Those are going to be a little bit more challenging, but it's the same ideas. And then the last thing we'll cover is these weird ones that have square roots in them. That'll probably be towards the end of the week. So, alrighty.
why are you staring at your